Hello there, and welcome to the video on the first half of section 4.9, where I'm going to be explaining how to find the general and particular antiderivatives of a function. And probably most folks don't know particularly what an antiderivative is, so I'm going to explain that to you in a moment. Hopefully, by the end of this video, you'll be very familiar with what that means and how to find it. Okay, so before I go into an explanation of what an antiderivative is, I'm just going to do kind of a cold opening and say, let's just start doing some math problems, and then I'll sort of go back and explain what the antiderivative definition is in mathematics. All right, so my first example here is example A. Let me zoom in just a little bit here. In this particular problem, I am given not a function, but I'm giving the derivative. So we're told the derivative, dy dx, is equal to x cubed. And we're asked, what is the function? What is the y function that would have led to the derivative being dy dx equals x cubed? So this is a thinking backwards problem. We know how to differentiate x cubed, but how do we go backwards and think about what would it have to have been in order that the answer is actually x cubed? And I am going slowly and saying this in different ways, partially to help explain it more clearly in different ways, but also to kind of waste a little bit of time, because I really want you to think about this. I really want you to think, what could the function be, right? Kind of think about it for a moment and see if you can come up with an answer. And then I will reveal my answer. All right, so many folks, when they work on this for a bit, they'll come up with some version of x to the fourth, because the derivative of x to the fourth goes down to x cubed. But we have a problem with the derivative of x to the fourth having a 4 in it. So if you put a 1/4 in front of this, when the 4 comes down, it will divide out with the 1/4, or cancel, as people say, and that will give the correct derivative. So just combine this together, 1x to the fourth over 4. I think the math people would just write it as x to the fourth over 4. They just combine the two things together. So if y equals x to the fourth over 4, it actually has the correct derivative of x cubed. So that is a function whose derivative is what we're looking for, x cubed. Did you find it? If you didn't, that's okay. But now you can kind of see the logic that we need to use to find this out. Now, unfortunately, this is not the only answer, because some of you may have realized that if I take my x to the fourth over 4 function and I put like a +1 after it, it still has the same derivative, because if I have a function that's added on, its derivative is 0. And so I still just have the derivative of x to the fourth over 4, which is still x to the third. So this is also works. And you may be realizing, oh yeah, there's other answers, right? I could have y equals x to the fourth over 4 plus any number, +2 or -7 or plus pi. So we're going to say plus any constant c. C is any constant. So when we're given the derivative equation and we're asked to go backwards to find the function, many times the best we can do is find a generic form for that answer. It has to be x to the fourth over 4, but you could add in any constant, and that would also still have the proper derivative. So that we started with the function and we went backwards, and we found this general form of the answer where it has to be x to the fourth over 4 plus some number. And this, in fact, is the only type of function, or general type of function, that has the correct derivative. All right, let's do part B. For part B, it says, suppose we have the exact same formula. So this is the exact same derivative formula, but we also know an additional piece of information. We also know that when x equals 2, that y equals 3. So we're given two pieces of information. We're given the derivative function, and we're also given a value of x and y. Well, from the previous problem, we actually know what y is. We know y is x to the fourth over 4 plus c, because we just did that thing. But because we're given some additional information, we can use that information to discover the value of C. Like any of these math problems with algebra that you've done in the past, if you have values of the variables, you can plug those in and see what other information you get. So if I plug in x equals 2, x equals 2 goes in for the x value, y equals 3 goes in the y value, of course, and that gives me what? It gives me 3 as a y value. X to the fourth would be 2 to the fourth over 4 plus c. 2 to the fourth over 4, I believe, is just 4. 2 to the fourth is 16. 16 divided by 4 is 4. Yep. And so I subtract 4 on both sides, and I get c is -1. So if I was given some additional information, I know what the value of c has to be. I know that the correct answer here is not y equals x to the fourth over 4 plus c, but x to the fourth over 4 plus a -1, or as a lot of math people would just say -1, right? Since plus a negative is just a minus. So given some additional information, given some particular values of x and y, we can get a better solution. All right, so now, as I promised before, let me explain what antiderivatives, general antiderivatives, and particular antiderivatives are. So anti is like opposite or going against. So this is the opposite of a derivative. Instead of finding a derivative, we're going to go backwards to find the original function the derivative came from. A general antiderivative is this one right here. This is the general antiderivative because it has just the form of the answers, right? We have the plus c in it. So general antiderivatives will always have that plus c in there, given the type of function that we're looking for. If we know some particular values of x and y, then we can find a particular solution. So this is a particular solution here. Particular solutions over here because we have a value of c this time. So this is a particular antiderivative because we're able to discover the particular value of c. So there's the definition of general and particular antiderivatives. Start with a derivative function, go backwards. You either get a plus c or you can discover the value of c, and that gives you your general and particular antiderivatives. All right, so let's do a few more examples here, and we'll do maybe a little bit of twist on the next page, but that's basically what this section, at least the first half of section 3.9 is about, is just experimenting with finding general and particular antiderivatives. The second half of 4.9, by the way, is just applications, like word problems, and I'll do that in the next video. All right, so let's do a few more examples, and then we'll be done with this segment. All right, so my next one here, let's got a little bit, there we go. Our next equation here is the derivative is equal to 2 divided by x. So let me maybe go a little bit bigger. So once again, I want you to think about what could be the function for the antiderivative of 2 over x. What's the function where I differentiate? I get 2 over x. Yeah, I'm pausing, hopefully for other people to pause as well. Of course, you can always pause the video, but I'm forcing a pause in here, hopefully encouraging you to think about it. The reason why is because, like, when you were doing algebra, like, remember when you were younger and you did like algebra and you did like x plus 4 and 2x minus 1, and you had to multiply those things out and you had to FOIL, and you got some like big answer. You got like 2x squared minus or plus 7x and then minus 4. So you eventually got probably pretty good at multiplying stuff out by distributing. But if I asked you to factor this thing, suppose you didn't know the answer, and I asked you to factor this thing, and you had to say, okay, I have to make 2 parentheses. It's a harder process to factor, right? Because it's a thinking backwards process. I have to think about what could the parentheses be. This has to be a 2x and an x, right? It has to be a 2 and a 2 or a 1 and a 4, right? Like what the factoring is a more complicated process. Antiderivatives are a more complicated process. It's essentially a thinking backwards process. And you're not going to get good at doing antiderivatives unless you practice it. Like, you're not going to get at factoring unless you practice it, right? I mean, there's some tips and stuff like that, but generally, practice is what you really will need to become good at it. All right, well, if I've talked enough and wasted enough time, the function whose derivative is 2 over x is 2 ln of x. I'm just going to write that without the absolute value bars, just to make things easier for us, plus c. So 2 ln x plus c is our antiderivative. It's our general antiderivative function. And you can always check this by differentiating 2 ln x plus c. If you differentiate 2 ln x plus c, you get exactly 2 over x plus 0, 2 over x. And if you've done the next part by chance, if you also know the point is 1 comma 5, we just plug that in. Remember, plug in the y for the y, plug in the x for the x. The ln of 1, if you don't remember that, you can use your calculator. It's equal to 0. And so we know c is 5. So we have now in a particular solution, our particular solution would be y equals 2 ln x plus 5. That would be our particular solution for this derivative equation with the knowledge that it has x equals 1 and y equals 5 as a point. All right, another opportunity for you to try. dy dx equals 3 sine x. That's example D. I'm not going to pause. I'm just going to let you pause if you want to try it. Let's see. So the answer for this one, I have to think backwards in my head. We know it's going to be a cosine, and it's got to be a -3. -3, because when I differentiate cosine, I get a negative, so it has to have a negative to undo that other negative. And then I do need a plus c, because no matter what constant I add in, +1, +7, whatever, when I differentiate that constant, it goes to 0. So that's the function. That's the general antiderivative. And then if I plug in the point, I plug in for the y value, I plug in 0 for the x value. If you don't remember the cosine is the x value at that radian measurement. So radian measurement of 0 has an x value of 1. So the cosine of 0 is 1, or you can use a calculator and punch it in if you don't remember the values of some of those trig functions. So cosine of 0 is 1. So we get this equation, and we solve for c, and we get 7. And that means that we have our final particular solution of -3 cosine x plus 7. All right, hopefully you paused that. Hopefully you got something like this, or at least you saw the steps to do in order to get the answer. And then, my friends, is antiderivatives, general and particular antiderivatives. Right? This was the general up here. Let me just write the words down. Oops. This was the general right here, just so people can connect the words to the answers. And this is the particular. All right, so I got a couple more examples for you. Not really too much different, but some little things that might be helpful when you're doing homework and more complicated looking problems. So in example E, if you look at this one here, I have given the second derivative. The second derivative is 12x squared minus e to the x, and I'm still looking for the function. So this definitely looks a little bit different, because before we were given the first derivative, and now we were given the second derivative. However, our process is really going to be the same. If we have the second derivative formula and we go backwards, we don't find the function, we find the first derivative. So if we're going to go backwards, do the antiderivative, we don't get y, we get dy dx. And then we have to sort of think backwards, what function would give 12x squared as its derivative? And it's going to have an x to the third, right? So that when you do the power rule, it becomes a 2. And then you have to think about what number this has to be to make 12. And I think people will figure out pretty quickly that the number 4 works, because when I bring down the 3, I get 3 times 4, which is 12. And e to the x is nice because the derivative of e to the x is e to the x, which means the antiderivative of e to the x is also e to the x, right? It's got to be the same. If the derivative is the same, then the antiderivative is also got to be the same. Now, it does not give me any values to plug in, So the best I can do is a general antiderivative. So I need a plus c there, right? I have to have a plus c because I don't have a way of discovering what that plus c is. And when I differentiate this plus c, I still get the same answer because the derivative of an added on constant is 0. So now I can go backwards again. If I have the derivative, I go backwards. That means I find the original function. I have to do the antiderivative of 4x cubed. That's going to have x to the fourth. And actually only needs a 1 in front. So you can put a 1 in front, or you don't have to put anything in front as you want, because the derivative of 1x to the fourth is, in fact, 4x cubed. The antiderivative of e to the x is still e to the x. The antiderivative of c is not 0. A lot of students forget about this. We're not doing derivatives. We're doing antiderivatives. So what function do I differentiate and get an answer of c? All right, if you had time to think about that, the answer is c times x. If I differentiate c times x, the derivative of 2x is just 2. The derivative of cx is just c. So that's the antiderivative of c. Any constant anti-differentiates to constant times x. Now, again, I don't have any numbers to discover the values of constants. And I did do an antiderivative of this, middle one here in blue, right? And so when I anti-differentiate, I get another constant. Now, if you put a plus c here, you will lose points because we don't know these two constants are the same. One constant could be 3, the other constant could be 4. So you're going to have to use different letters. You can use like a C1 and a C2, or a C and a K, whatever. Just make sure they look different because they don't have to be the same constant. But you do need a constant there because when I differentiate this y function, the derivative of the plus k is 0. And so this is still the antiderivative. So this right here, my friends, is the function. This is the general antiderivative. This is the function whose second derivative is the one that was given to us. And I have to be given a bunch of information to discover the value of c and or k, and that is the next part. Okay, so right down below, let me just shrink this a little bit. It says, what if we also know the value of the derivative when I plug in x equals 0? So the value of dy dx when x equals 0 is equal to 1, and the value of the function when I plug in x equals 0 is equal to 2. So they're giving us information here about the value of the derivative and about the value of the function. Well, if you're given numbers, again, that's our cue in algebra to plug things in. So this goes into what equation? This tells us something about the derivative. When I plug in x equals 0 into the derivative equation, I get 1. So that has to go into the derivative formula, right? That's where I plug in this in. So the derivative formula, I plug in dy dx, I plug in x equals 0. So I'm going to gain 4 times 0 cubed minus e to the 0 plus c. And dy dx is equal to 1, right? So the way we read this is the value of the derivative is 1 when I plug in x equals 0, right? We don't say it that way grammatically, but the derivative when I plug in x equals 0 has a value of 1. It looks like this equation here in green. And then we could simply just solve this thing. 4 times 0 is 0. E to the 0 is 1. And then I find out the value of c is equal to 2. So now I know the value of c. C is not a mystery anymore. So that means I can improve my general antiderivative formula because I can now write in the value of c. So I'm going to do that. I don't know k still, but I do know the value of c. So that's my value of my function. Now I'm given more information. So I'm going to take this more information. This says when I plug in x equals 0 into the y equation, I get 2. Here's my, you can plug it into the old y equation if you want, but I'm going to plug it into the new improved y equation because it has, did anyone notice I wrote 2c instead of 2x? Hopefully you did. C is 2, right? So for some reason, I just wrote c instead of x. Little brain distortion there. So let me fix that. Since we know the value of c, we plug in 2 for c. C is 2. Thank you. So now I'm going to plug in x equals 0, and I only have one thing left to find, which is the k. So the y value is 2 when I plug in 0. And now I can solve for k. and that gives me a k value of 3. And then I get my final answer. So my final answer is going to be y equals x to the fourth minus e to the x plus c times x, which is 2 times x, plus k, which is plus 3. So here's an example where they start with something looking much more complicated. They start with the second derivative. It is more work, but it's sort of the same process. You can do the antiderivative to go backwards a step to the first derivative and do it again to go backwards to the original function. You do have to remember the plus c each time, or plus c plus k, or whatever version you want that. Just don't put plus c both times, because that will be not correct, since we don't know. Like, I mean, they weren't the same this time. One was 2 and one was 3. So there's a good example where you don't know they're the same number, so you can't use the same letter to represent that plus thing. All right, and then one last example I have here: find the antiderivative of this function. Excuse me. This is a complicated function. It has a fraction. We're thinking like quotient rule, right? Because like quotient rule is how you differentiate fractions, but it's probably also how you get a fraction when you differentiate a function, right? So thinking back, this is hard. It's gonna be hard thinking of what function makes the quotient rule or whatever rule give you this. So one of the things we're going to be doing in the next chapter is trying to find ways to simplify our function before attempting to find an antiderivative. It's going to be very imperative for us to simplify these things, because it's just too hard going backwards with all the different possibilities, all the different function types, all the different rules and stuff. It's just too much without being able to simplify a lot of these things. So I chose this one because it has an algebraic simplification. You may have seen this before. Actually, it was a similar problem was on the very first lab assignment that y'all worked on in this class. This can be simplified using the distributive property. We have everything being divided by x, so we can divide each thing by x, right? We can just divide everything by x. That's what the over x means. It means everything's being divided by x. So my function, x squared divided by x is x, 2x divided by x. I'll just write it out. I'll write it out. How about that? It's x squared over x minus 2x over x plus 3 over x. So my function is x minus 2 plus 3 over x. Now, we're supposed to find the antiderivative of this, and it's somewhat confusing. Math people are oftentimes confusing this way. We know the antiderivative finds the function given that this is a derivative. So even though they've written fx equals this thing, this is really the derivative of something, right? This is really some dy dx type thing, right? We got to be thinking of this as a derivative because we're going backwards from the derivative to the original function. The problem is they oftentimes write the derivative function as fx because I guess, officially the derivative is a function. It would be so much nicer if they write this as f prime x. Then it would just be a little easier for us to sort of parse out. But math people aren't always kind that way, so you're going to have to just kind of, be on guard and make sure you understand what's going on. So this is really a derivative equation. So we can go backwards and find the original function. The way the mathematicians will write the original function, if they give f of x as the derivative, they will write the antiderivative with a capital F. So it's just the way the math people do things. So if the little f is supposed to be the derivative, then the capital F is supposed to be the original function. So if this was dy dx, as it should have been written, then this is really y. So it's kind of going backwards like that. All right, so that's a little clarification, hopefully, with the strange notation that you may see in this section. And then once again, we just have to do the antiderivative of each of these things. The antiderivative of x squared over 2. The antiderivative of 2x. The antiderivative of 3 over x, 3 ln x. Officially, it's the absolute value of x. We're not going to be worried too much about absolute values at this point. We're just trying to figure out antiderivatives. I'll add in the absolute value stuff a little bit later when we get more comfortable with the antiderivative stuff. Don't forget, when you're doing an antiderivative, you always get a plus c because the derivative of plus c is still 0. So that is our general antiderivative formula. And unless they gave us some values to plug in, we're done. That's it for that problem. All right, that's it for this video. hopefully this was helpful, and now you feel like you know how to find antiderivatives. But if you have any questions, please reach out and let me know, and I'll help you some more. All right. I hope you have an enjoyable day.